Okay, hi everyone, welcome back to this live stream. We'll be continuing our discussion on Windows Server 2003 administration. So the screen, and here we go. Microsoft's network components and the OSI model. Because the OSI model is so abstract, it can be hard to tell how its concepts relate to the actual network software and hardware you use in the real world. The following sections will make the link clearer. We will introduce you to the specific protocols that are included with Windows Server 2003 and see how they apply to the various layers of the OSI model: device, drivers, and the OSI model. Every hardware device in a computer requires a software-based device driver to make it work. Some drivers, for instance, the driver for an integrated device, electronics, IDE, hard disk, or for the keyboard are built into the operating system. Other devices require that drivers be installed separately when the device is attached or installed in the computer. Windows Server 2003 really blurs this distinction because it includes drivers for several hundred different network cards, but if your card isn't on the list, you will need to install drivers provided by the manufacturer. In the past, when Windows 3.11 was introduced, network drivers were vendor specific for both operating system and the card. You might, for instance, have a difficult time if you wanted to put a 3COM Ethernet card and an IBM token ring card in the same server. Worse yet, most drivers could only be bound to a single protocol stack and a single card, so you couldn't have two cards using TCP/IP on one server. A variety of vendors tried to solve this problem by developing driver interfaces that allowed multiple cards to be bound to multiple protocols. Apple and Novell developed the Open Data Link Interface (ODI), and Microsoft countered with the Network Driver Interface Specification (NDIS). Microsoft's operating systems have supported NDIS ever since, making it possible to bind either multiple protocols to one card or the same protocol to multiple cards. Network adapter cards and drivers provide the services corresponding to the data link layer in the OSI model. In the IEEE model, the data link layer is split into the logical link control LLC sublayer, which corresponds to the software drivers, and the media access control MAC sublayer, which corresponds to the network layer. You can think of the drivers as intermediaries between the higher layers and the card hardware that handles the business of forming packets and stuffing them into a wire. The basics of network protocols. Protocols are nothing more than an agreed upon way in which two objects, people, computers, home appliances, etc., can exchange information. There are protocols at various levels in the OSI model. In fact, it is the protocols at a particular level in the OSI model that provide that level's functionality. Protocols that work together to provide a layer or layers of the OSI model are known as a protocol stack or protocol suite. The following sections explain how network protocols move data between machines. How protocols work. A protocol is a set of basic steps that both computers must perform in the right order. For instance, for one computer to send a message to another computer, the first computer must perform the steps given in the following general example. 1. Break the data into small sections called packets. 2. Add addressing information to the packets identifying the destination computer. 3. Deliver the data to the network card for transmission over the network. The receiving computer must perform these steps. 1. Accept the data from the network adapter card. 2. Remove the transmitting information that was added by the transmitting computer. 3. Reassemble the packets of data into the original message. Each computer needs to perform the same steps in the same way and in the correct order so that the data will arrive in a and be reassembled correctly. If one computer uses a protocol with different steps or even the same steps with different parameters such as different sequence, timing, or error correction, the two computers won't be able to communicate with each other. Network packets. Networks primarily send and receive small chunks of data called packets. Network protocols construct, modify, and disassemble packets as they move data down the sending stack across the network and back up the OSI stack of the receiving computer. Packets have the following components: a source address specifying the sending computer, a destination address specifying where the packet is being sent, instructions that tell the computer how to pass the data along, reassemble information if the packet is part of a longer message, the data to be transmitted to the remote computer, often called the packet payload, error checking information, ensure that the data arrives intact. These components are assembled into slightly larger chunks. Each packet contains 3 distinct parts listed here and seen in figure 1 to 12, and each part contains some of the components listed previously. Header. A typical header includes an alert signal to indicate that the data is being transmitted, source and destination address, and clock information to synchronize the transmission. Data. This is the actual data being sent. It can vary depending on the network type from 48 bytes to 4 kilobytes. Trailer. The contents of the trailer or even the existence of a trailer vary among network types, but it typically includes a CRC. The CRC helps the network determine whether or not a packet has been damaged in transmission. So figure 1.12, a packet consists of a header, the data, and the trailer. Protocols and binding. Many different protocol stacks can perform network functions, and many different types of network interface cards can be installed in a computer. A computer may have more than one card, and a computer may use more than one protocol stack at the same time. The binding process is what links the protocol stack to the network device driver for the network interface adapter. Several protocols can be bound to the same card. For instance, both TCP, IP, and AppleTalk can be bound to the same Ethernet adapter. In addition, one computer with several interface adapters, for instance, a server that must be able to communicate with both a local area network and a network backbone, can have the same protocol bound to 2 or more network cards. The binding process can be used throughout the OSI layers to link one protocol stack to another. The device driver, which implements the data link layer, is bound to the network interface card, which implements the physical layer. TCP/IP can be bound to the device driver, and the NW-link session layer can be bound to the device driver. Bindings are particularly important to Windows Server 2003 because you'll often want to change the bindings so that protocols don't need on a particular network aren't bound to some network adapters. For example, it's very common to unbind the NW-link protocol from the network card connected to a web server's internet connection. Determining connections. There are 2 ways that communication between computers can be arranged: using connectionless protocols and using connection-oriented protocols. It's important to understand the difference between them because different Windows Server 2003 services use both types connectionless protocols. It might seem odd to talk about a connectionless protocol for networks, but you use at least 2 of them just about every day: radio and television. Connectionless systems assume that all data will get through, so the protocol doesn't guarantee delivery or the correct packet ordering. Think of shouting a message out your window to someone walking by outside. There's no guarantee that they'll hear you, but it's quick and easy. These optimistic assumptions mean that there's no protocol overhead spent on these activities, so connectionless protocols tend to be fast. The User Datagram Protocol (UDP), which is part of the TCP/IP protocol standard, is an example of a connectionless Internet Transport Protocol. Connectionless systems normally work pretty well on lightly loaded networks, likely most local area networks. Unfortunately, they break down quickly in large or heavily loaded networks where packets can be dropped due to line noise or router congestion. All is not lost for connectionless transports, however, because higher level protocols will know that data has not reached its destination after some time and request a retransmission. However, connectionless systems don't necessarily return data in sequential order, so the higher level protocol must sort out the data packets. Connection-oriented protocols. Connection-oriented systems work more like your telephone. You have to dial a number and establish a connection to the other end before you can send a message. Connection-oriented protocols pessimistically assume that some data will be lost or disordered in most transmissions. They guarantee that transmitted data will reach its destination in the proper sequence and that all data will get through. To establish this, connection-oriented protocols retain the transmitted data and negotiate for a retransmission when needed. Once all the needed data has arrived at the remote end, it can be reassembled into its proper sequence and passed to the higher level protocols. This means that any application can depend on a connection-oriented transport, reliable delivery, data exactly as it was transmitted. Transmission Control Protocol (TCP) is an example of a connection-oriented internet protocol. For local area systems where data isn't likely to be dropped, it makes sense to publish serialization and guaranteed delivery up to higher level protocols that are less efficient because they won't be used often anyway. But in wide area networks like the internet, it would simply take too much time for higher level protocols to sort out what data has been sent and what was missing. So the transport protocol simply takes measures to guarantee that all data gets through in order. Network protocols and Windows Server 2003. So far, you've been reading a lot of abstract material that seem pertinent to Windows Server 2003. Now we'll show you the network protocols included in Windows Server 2003 and how each fits into the models you have read up to this point. There are a number of protocol stacks used in world networks today. Besides network, AppleTalk, NetBIOS, and TCP/IP, there are a bunch of specific specialty protocols like IBM's Systems Network Architecture (SNA), Digital, now HP Compact's DECnet, and others. Even though these protocols actually work at different levels of the OSI model, they fall neatly into three distinct groups as seen in the following list and in figure 1.13. Application protocols provide for application-to-application interaction and data exchange. Transport protocols establish communication sessions between computers. Network protocols handle issues such as routing and addressing information, error checking, and retransmission requests. Microsoft networking products come with three network transports: NWLink, IPX, SPX, AppleTalk, and TCP/IP, and each is intended for networks of different sizes with different requirements. Each network transport has different strengths and weaknesses. NWLink is intended for medium-sized networks in a single facility perhaps, or for networks that require access to novel network file servers. AppleTalk's primary use is for interoperating with Macintosh computers, a topic that's too specialized to discuss further here. TCP/IP is a complex transport sufficient for globe-spanning networks such as the internet, and Microsoft is doing everything possible to position TCP/IP as one of its size fits all network protocol. TCP/IP is required to use Active Directory and is the default protocol for Windows Server 2003. Note, Windows Server 2003 does not include for the now defunct NetBEUI protocol. NetBEUI was not routable and Microsoft deemed the protocol unsuitable for enterprise scale networks. 1.3. The OSI protocol stack can be simplified by grouping its layers into three. So we'll start with physical layer, data link layer, network layer, transport, session layer, presentation layer, application layer, application. NWLink IPX SPX is Microsoft's implementation for Novell's IPX SPX protocol stack, which is used in Novell Network. In fact, it's fair to say that NWLink IPX SPX is nothing more than IPX for Windows. NWLink IPX SPX is included with Windows Server 2003 primarily to allow Windows Server 2003 to interconnect with legacy Novell network servers and clients. Microsoft clients and servers can then be added to existing network installations over time, easing the migration between platforms and obviating the need for a complete cut over from one networking standard to another. The advantages of NWLink IPX SPX include the following. It's easy to set up and manage. It's routable. It's easy to connect to installed network servers and clients. However, NWLink IPX SPX has some disadvantages, such as these. With NWLink IPX SPX, it is difficult to exchange traffic with other organizations. It has limited support in Windows Server 2003. It doesn't support standard network management protocols. Truly large networks that connect many organizations may find that NWLink IPX SPX is difficult to use because there's no effective central IPX addressing scheme as there is with TCP/IP. To ensure that these networks don't use the same address numbers, IPX doesn't support the wide range of network management tools available for TCP/IP. TCP/IP is actually two sets of protocols bundled together: the Transmission Control Protocol TCP and the Internet Protocol IP. TCP/IP and a suite of related protocols were developed by the Department of Defense Advanced Research Projects Agency, ARPA, or later DARPA, beginning in 1969. The original goal was to develop network protocols that were robust enough to route communications around damage caused by nuclear war. That design goal was never tested, but some aspects of that design have led to the redundant distributed whole we call the Internet. TCP/IP is by far the most widely used protocol for interconnecting computers, and it is the protocol of the Internet. This is because although ARPA originally created TCP/IP to connect military networks together, it provided the protocol standards to government agencies and universities free of charge. The academic world leapt at the chance to use a robust protocol to interconnect their networks, and the Internet was born. Many organizations and individuals collaborated to create higher level protocols for everything from news groups, mail transfer and file transfer to printing, remote booting, and even document browsing. TCP/IP is currently the protocol of choice for most networks because of its rapid and widespread adoption. TCP/IP is used for networks that span more than one metropolitan area or to connect to over the Internet. TCP/IP has some significant advantages: broad connectivity among all types of computers and servers, including direct access to the Internet, strong support for routing using a number of flexible routing protocols, support for advanced name and address resolution services, which will be covered in more depth later in this book, the domain name services DNS and dynamic host configuration protocol DHCP, and the Windows Internet Name Service WINS. Support for a wide variety of Internet standard protocols, including protocols for mail, transport, web browsing, and file and print services, centralized network number and name assignment, which facilitates internetworking between organizations. TCP/IP has some disadvantages. It's harder to set up than IPX. Its routing and connectivity features impose relatively high overhead. It's slower than IPX. Even given these disadvantages, it's the core protocol that Windows Server 2003 depends on for all its network services. In fact, most of this book focuses on TCP/IP and related services. TCP and UDP relies on port numbers assigned by the Internet Assigned Numbers Authority, IANA, to forward packets to the appropriate application process. Port numbers are 16-bit integers that are part of a message header and identify the process that the packet should be associated with. For example, let's say that a client has a copy of Internet Explorer and a copy of Outlook Express open at the same time. Both applications are sending TCP requests across the Internet to retrieve web pages, email, respectively. How does the computer know which packets to forward to Internet Explorer and which packets to forward to Outlook Express? Every packet destined for Internet Explorer has a port number of 80 in the header, and every packet destined for Outlook Express has a port number of 110 or 110 in the header. Table 1.1 contains a list of the major port numbers you might need to know for the exam. You can also visit www.ina.org to get the most current full list of port numbers. So here we are now, table 1.1, port number and description 20, file transfer protocol, FTP data 21, file transfer protocol, FTP control 23, telnet 25, simple mail transfer protocol, SMTP 80, hypertext transfer protocol, HTTP web 88, Kerberos 1110, post office protocol v3, POP3 443, secure HTTP HTTPS. So I'm going to leave it here today for this video. If you like listening, for spending some time with me, and I hope you have a nice evening. Thank you.